Hello, yeah, my name is Uday, and this is a quick video to explain about my second assignments. They are like 10 questions, five are like derivation part, and five are like coding implementation using PyTorch and uh, data science techniques and machine learning techniques. So today I'll explain you my first question, which is like elbow from KL divergence. Okay, now I'll explain how the divergence lower bound or elbow is derived from the KL divergence in variational encoders. We start with the KL divergence between the approximate posture Q Z by X and the true posture of P of Z by X by using Bayes rule. We express like P of Z by X as P of X comma Z by P of X and plug that into the KL divergence formula. When we rearrange the terms, we'll get like log P of X equal to elbow plus KL divergence of Q of Z by X with P of Z by X. Here the elbow is expected the long joint likelihood minus the entropy of the approximate posture. Since the KL term is always a non-negative, the elbow becomes a lower bound on log P of X. So if we maximize the elbow, we will essentially minimizing the KL divergence, which means our approximate posture is getting closer to the true one. This is why optimizing elbow is central to learning in VAEs. It helps us to train deep generative models in a traceable way. Uh, uh, that's the institution and math behind the elbow. Now I'll explain you about the my second question, which is KL divergence between two Gaussians. Uh, I'll explain the analytical KL divergence between the two multivariate Gaussian distributions. Let's say Q of Z equal to natural of mu Q and sigma Q, and P of Z equal to natural number n of mu P and sigma P. The KL divergence between them is like uh, KL divergence of Q parallel P equal to 1 by 2 log of sigma P by sigma Q. Absolute, yeah, it's absolute minus K plus PR of sigma P power to minus 1, comma sigma Q plus mu Q minus mu P to the power T, like transpose, and sigma P power of minus 1 into mu Q minus mu P. In variational autoencoders, we usually assume P of Z equal to natural numbers of 0 to I and Q of Z by X equal to mu of n a natural number of mu and a diagonal sigma square. The KL the KL amplifies to 1 by 2 sigma from I equal to 1 to K, yeah, of sigma I square plus mu I square minus 1 minus log sigma I square. This term encourages the encoder to keep the latent distribution close to the prior. It acts as regularizer and enables effective sampling during generation. And that's the KL divergence between the Gaussian, compact, analytical, and the central to VAE training. Now I'll explain you the third question KL term as a regularizer in the elbow. I'll explain the role of KL divergence in terms of VAE loss function and what happens if you remove it. The VAE loss or the elbow has the two parts that reconstruct the term and the KL divergence term. The KL term measures how far the approximate posture Q of Z by X is from the prior P of Z. Usually the standard norm it acts like a regularizer encouraging the latent space to stay smooth and well behaved. And the impact is like without the KL term, each input can get mapped to an arbitrary region in the latent space that breaks the generative ability. The sampling from the prior won't produce meaningful outputs, and the latent space become disorganized. So the KL term essential for making the VAE a true generative model. It ensures generalization structure in the latent space and enables reliability sampling. So this is for the third question. And now I'll explain you the fourth question, which is the mode collapse in GANs. I'll explain like why GAN suffer from the mode collapse and how we can fix it. The GAN optimize is a min-max objective where the generator tries to fool the discriminator, but sometimes the generator finds a shortcut. Uh, it learns to produce only one of your outputs that is the discriminator, even if they don't capture the full data distribution. This is called the mode collapse. The mathematically the generator updates using the gradient of log of 1 minus d of g of z, which can vanish if the discriminator becomes too confident. So the generator gets stuck generating the limited modes. We can prevent the mode collapse using the methods like Wesset and GAN, which provides a smoother gradients or mini batch discrimination, which penalizes the lack of diversity. Other fixes include feature matching, and unrolled GANs, all with strong mathematical motivation. That's how GAN fall into mode collapse, and that we guide them out. Yeah, now I'll explain you the fifth question, which is a posture collapse in VAEs. I'll and how we can address it. Like the posture collapse happens when the encoder outputs the Q of Z or Z by X becomes identical to the prior P of Z, typically a standard normal. This means the latent variable Z carries no information about the input, and the decoder learns to reconstruct the X without using Z. I'll tell you like why this happens. Mathematically, this occurs when the KL divergence term in the elbow dominates, pushing mu of x to 0 and sigma of x to 1, minimizing the KL term to 0, but the cost of the informative latent variables. We can fix this using the KL annealing, which gradually increase the KL term during the training or free bits, which enforces a minimum KL for each latent dimensions. Architecturally tweaks with weaker decoders and skip connections that also prevents the collapse. This is how the VAs can collapse and how we can fix it. Yeah, now I'll explain you the fifth question in the part two assignment, which I'll also do the code implement. So I'll explain you the question and answer. Like it's a optimal discriminator and the Jensen-Shan divergence. Uh, let's look how we derive the optimal discriminator for a GAN and connect it to JSD. Yeah, shortcut for the Jensen-Shan divergence. The GAN objective is a min-max game. We fix the generator and maximize the discriminator. The equation is like d of x we pass to p data into log d of x plus e of x to p of generator into log of 1 minus d of x. Taking the derivative and setting it to 0 gives the optimal discriminator. The d star x equal to p data x by p data x plus pg x. The JSD connection, when we plug D star X into the original GAN objective, it simplifies to V of T star G equal to minus log 4 plus 2 into JSD of P data to PG. This shows GAN training minimizes the JSD between the real and generated distributions. So by learning the optimal discriminator, a GAN minimizes the JSD, aligning the generated samples with the real data. This is the explanation of my questions. Thanks for watching. Bye.